Hi everyone, this is Tom Cherryholmes with a new video series. There was some discussion a while back as to the efficiency of the routines inside of the operating system in every single Amiga. I pointed out that these routines were initially designed when the Amiga was still a game console, and thus that these routines were intended to be used to write games. And there are a whole bunch of wonderful routines that are sitting inside each and every single Amiga, including but not limited to audio routines, graphics routines for drawing all sorts of graphics on the screen, and even a multi-planar animation system that can combine background graphics, blitter objects, and sprites all together and animate them seamlessly. Somebody basically said, well, if you think these routines are so good, why don't you use them to implement a game? So I thought, okay, sure, we can do that. And so I decided to think, okay, what would be a good game, simple enough to actually implement, that could show all of the bits and pieces in concert? And the game that I came up with was PAC-MAN. So the goal with this particular series is to show my development process of going through and implementing all of the bits and pieces that are needed to implement a game of PAC-MAN, using the operating system routines, and winding up with a piece of software that can run on each and every single Amiga, starting with, but not limited to, an original Amiga 1000 with just 256K of chip memory and Kickstart 1.1, all the way up to an Amiga 4000 with a 68040 or faster, and be able to run the game multitasking along with other applications. So what do we have access to? Turns out we have access to a lot. One of the things that was very instrumental in the development of the Amiga and software development in general for the Amiga were the ROM kernel manuals. Of course, we have the hardware reference manual, and the hardware reference manual is extremely useful because it gives us comprehensive outlines of every bit of hardware inside the Amiga, along with the registers that you need to hit in order to do certain things. And this particular manual was copied to a great extent by other programming manuals, particularly those in Europe, where people were used to programming 8-bit machines, such as the Commodore 64, the Atari 8-bit, or the ZX Spectrum, and dealing with these things on a register-by-register basis. And indeed, if you use the hardware directly, you will maximize your usage of what you can do with the CPU and the custom chips. But there has been a great deal of thinking, especially in the late 80s to early 90s of game development, when pretty much most of the Amiga systems that were out there pretty much had the same basic configuration, that it was safe to basically just take the operating system and throw it away, revector everything toward your own code, and just use the hardware directly. And while this does give you maximum performance, it doesn't come without its disadvantages. One of which is that you really can't run the game alongside something else, because a game takes over your system. And because the game is directly talking to your hardware, it is often, for the sake of simplicity and expediency, locked down to a particular hardware configuration, meaning that it assumes that you have at least a certain amount of memory, and probably doesn't know that you may or may not have more than one disk drive to use for your game, among other things. And this is fine, especially when you consider that especially back in the day, when those of us that were doing game development at that time, we were definitely on a time schedule. So it was very much looked upon that you would take and make a game for a particular processor, say a 68,000, and try to use that 68,000 based code wherever you could do so, taking and adjusting for all of the various registers to match your target system, and in many cases doing things like using these hardware registers to create a platform environment similar to another machine, such as an Atari ST, because it also had a 68,000. Yeah, I mean, this was a valid way of handling things and doing things. But it, again, it had its issues. And it was especially, at least in my opinion, very wasteful, because you wound up throwing away so much of what was sitting inside the system to begin with. Everything from a fully multitasking kernel, able to run hundreds of tasks at once, very seamlessly, very fast, very effectively, to a complete animation system, able to handle a whole bunch of different types of animating objects. Everything from virtualized sprites to blitter objects, using the blitter to take and move things across a playfield very effectively, interacting with playfields, to just using the hardware sprites directly. All sorts of different combinations of things that you could do in concert with the exec, making different tasks, having those tasks handle each individual game character, for example, taking and sending messages back and forth, that sort of thing. But also, you also had intuition. And intuition, sorry, my bad. And intuition gave you a whole host of wonderful abstractions for dealing with all of the different aspects of the hardware and dealing with a multitasking environment effectively, especially one like a computer where you had different windows with wanting to take and mix screen resolutions and different color palettes, etc., taking care of all of the heavy lifting for all of those things and making it much simpler to program. And the version of PAC-MAN that I'm working on here is essentially going to be using these individual elements here. I know this has been an extremely long discussion here, and I think I'll just end it right here by starting to show some practical elements here. But I wanted to kind of give context to what I'm trying to do. Apologies if I rambled on too long. We'll use my development environment that I used for the Amiga as a workstation video here, and we'll go into my hard disk. And in my workspace, we now have a PAC-MAN folder. And the PAC-MAN folder essentially has what are essentially a whole bunch of different test harnesses for different parts of the game. And as I take and build different aspects of the game, they're all going to be built out in separate units, such as handling sprite animation, handling drawing the individual stages that we may be currently on, doing the maze drawing, as well as different tutorial programs that kind of show different aspects, such as how bitplane graphics work, and so on. And as we do these individual bits and pieces, we get them debugged. The goal is to take and split out the individual pieces that are in these bits of code and to turn them into tasks. Or, we can think of tasks now today as threads or lightweight processes that run under the Exec microkernel that form the basis of the game, communicating back and forth using MessagePorts. We really won't go into screen task because I don't have that one ready just yet. That'll be in the next video here, but we'll start by looking at, for example, DrawMaze. And DrawMaze essentially shows the maze drawing routines here, and this uses the intuition border routine to take and draw the maze. It will delay here for a few seconds, and then once it's done, it will take and exit automatically. But you can see right there that it was able to take and draw the entire maze, and the entire maze is actually being drawn as a series of borders, that is, line drawing vectors. Borders traditionally are used inside of Intuition to draw things like button borders or borders for input fields and proportional scroll bars, etc. But here I am literally using it to take and draw each individual section of the maze. We draw the maze borders all the way around, and then each one of these links to the next one. And then the individual maze features, the different corners, the different edges, the different pieces inside the maze that create the various tunnels. And if we actually take and look inside of it a bit more, we'll take and, sorry, I accidentally closed it. We will look at what is a border. Well, if we look at what a border actually is, it's just a structure that Intuition wraps around polylines in order to take and do control borders and things. And if we actually take a look at if I can go, I really need to take and make bookmarks. Hold on one moment. Let me pause for a second and find the right page. Okay, there we go. Sorry about that. It takes forever for the PDF renderer to actually take and render out individual thumbnails so I can see where I need to go. We have a number of different abstractions inside Intuition that we can use to our advantage to take and draw images, as well as doing line drawing and text. And for this, we actually are going to take and create borders. And it's a data structure called a border. It's just a general purpose structure for drawing connected lines at any angle and rendering any arbitrary shape made of groups of connected lines. And all they are essentially just start here, draw to here, and so on, and so on, and so on. And you can take and connect, you can take and link multiple borders together for one DrawBorder command, one DrawBorder function to take and render all of the different borders on the screen. And this is all a border actually is. It's a structure consisting of, okay, where do we want to put this relative to the left edge and the top edge? What pins do we want to use? That is the foreground and the background pins. And what draw mode do we want to use? Jam 1 or Jam 2, whether or not we want to take and replace the background or the foreground and the background. How many elements are inside the border? The pointer to the data, and of course, since this is built as a linked list, we have a pointer to the next border to render, so we can render multiple borders. And that's all we really have here. So in each of these cases, we start here at 0, 0, border of F20, okay, 4, 32 segments, and it's represented by BOF20. And if we look at F20 right here, we can see the coordinates right here. Since I picked 0, 0, it's literally starting at the top portion of the screen, and therefore the coordinates here are absolute screen coordinates. It was so I could take and port this directly from the mindset. And that's it. How many points can you have inside a border? Well, it turns out you can have up to 127 distinct points inside a border object, inside the border data, before border gives up and decides not to render it. It's good to know. It's something I found out while doing this. And that's all essentially DrawMaze is at the end of the day. It's just taking and rendering out that border as quickly as possible. So there we go. We can make this faster by basically taking and double buffering it, or we can take and render it off screen and blit it on. There's a few things that we can do here, although I think even at this point, the rendering speed is acceptable. You can also see right here that I'm using a custom font, and that custom font is actually being rendered inside the Amiga font editor. Matter of fact, if I go ahead and just launch it here, we can kind of go take a look at it. I'll take and launch another instance of WinUAE. I'm doing this because FED cannot run under Kickstart 1.1, rather the version that I have, so I just have to load it in another environment. No big deal. Let's go ahead and just load it in place here. It's loaded. Okay. I want to make one little change because normally I run this in PAL. I'll run it in NTSC, and we'll just start it here. The other window is right back behind. This is my 1.3 environment with a few extras tacked on, such as WShell and file name completer. Now, if I take and go to System and we go to Tools, go into our font editor here, we can see the font that's being rendered. Let's open up that font. Let's see what we got. And the font is actually called Arcade. I'll just go down to it here. And it's a single point size. It's 8 points. We load it. And here it is. And as I get more elements loaded in, we'll take and use it. And since I'm using this in low res, I go ahead and flip on the low res here so we can see the individual bits and pieces. And let's zoom in a little bit here. So there we go. I just go through and literally implement based on the font that's in the ROM and go ahead and draw out each individual font element as I need it. And it's implemented as a standard Amiga font, so it can be used as a standard Amiga font. And more to the point, you actually can use a piece of software called Font Dump. Sorry, oops, excuse me. You can use a piece of software called Font Dump to take and dump the resulting font into a form that you can use on your system here. Oops, okay, sorry, I moved it around here. But the point is, we wind up with a font structure that looks like this. Of course, we have the individual font stripe data right here. This is literally as it's rendered in bitplane memory. And then we have a text font structure, and this is normally what gets loaded in when you take and load a font using the disk font library. It takes and creates this structure, loads it in off the disk, fills in the structure here, and then calls the add font to add it to the system. Well, as it turns out, you can, believe it or not, take and initialize the data structure and then pass the resulting data structure that you just initialized in as arcade font. And then you can set that font as the default font for a screen or a window using text attributes. So if we look at font, we just create a text attribute section for it here. Arcade8.font, 8 pixels. It's a normal font, and we say that it is designed. And if we actually look at the text attributes for font in Intuition, we will find, for example, we will find that this basically states that any font that you put with this attribute here, don't scale it, but use the font at the size that it's intended. So, anyway, One of the other things that we do here is that we have a color table, which is just essentially the color palette that we're going to use for this particular screen here. And we use load RGB4 to take and load it in. And that brings us essentially to what each test harness is essentially doing here. And it's all pretty much doing the same thing. We come in, do a GFX base, okay, great. If not GFX base, okay, fine. Do all the basic initialization, load the graphics libraries, which for anything that we need to use from the operating system here, we need a handle to it. We get a base pointer to it, we get a handle to it, we open it up, and if it fails at any point, we bail out. Otherwise, initialize our fonts, set them to the screen. Then when we open the screen, it will use our font by default, load in our color tables, do our open windows. I go ahead and set Rast, which basically fills the screen a given color. In this case, it's just black. And then and one single command here will take and draw the entire maze based on the linked list data that you saw above. We then wait 600 seconds. We remove the font. Okay, PAC-MAN, okay, close window, close screen. We close everything in the opposite order that we opened it. So, there we go. That's DrawImage in and of itself. So you can see right there that we were able to use something built into Intuition to take and render out the mazes for us and do so in a very memory efficient manner. So if we actually take a look, for example, the compiled size of this particular piece of code is a little less than 7K, and that's with the runtime and everything else. There's bits and pieces of things that need to happen, the startup code and whatnot, that get linked in with C and everything else. And that's about as good as any time as I need to take and show a little bit of my Makefile structure here. This is just a script that gets executed, and I run it in the shell to take and compile it. And I'm using Lattice C 3.03 to take and do this build. This was the first C compiler that was available for the Commodore Amiga here, and I'm using this both for the case of historical accuracy and context, but also as a challenge, and just basically to show that this was how we did it back in the day, very, very early on, and I mean very early on. So the C compiler runs in two passes. You've got LC1 and LC2. LC1 takes and compiles the code down into an intermediate language, which it calls quads, creates a quad file, which is essentially just intermediate byte code. And then the second pass of the compiler takes the intermediate byte code and creates the individual object files. Now here is where you may have seen this particular method used on other compilers and other systems, and in point of fact, this is actually what happens with modern compilers like GCC and whatnot. It's just all abstracted by the front end, GCC or whatever. One thing that you won't see anywhere else but on Amiga-based specific systems are tools like Atom. And very early on, the linker that was available for the Amiga was called A-Link, and A-Link would take the individual object files and produce a runnable executable from them, linking against the Amiga library, linking against the Lattice C library for things it needed to, but also against the startup code. But we have to take and add some additional information into the object code that we just compiled to specify that we want the data structures that we have in these files here to go into chip memory by default, and for any code to just go into public memory, which can be either chip memory or fast memory, whatever is available, to run as efficiently as possible. So we use Atom and we say, okay, take drawmaze.o, create drawmaze.atom.o, and say any program code goes into chip memory, and any program code goes into public memory. Any data and BSS segments go into chip memory. That creates our Atom file, which we then take and subsequently link to. The only other consistent thing with all these test harnesses here is that I made the world's quickest icon just using the icon editor here so I could take and run the programs directly from the workbench. And that's the same case for every one of these. So now we've seen how DrawMaze is actually put together. Some of the other bits and pieces that we know we also need to do. Not only do we need to take and draw borders for the mazes and whatnot, we also need to draw various graphic images, such as what current stage that we're on. So we have a test harness here for something we call DrawStage, and you can see right here we have an algorithm here that takes and places the current stage down below, and just like the arcade, it only shows 7 elements. And once we show more than 7 elements, it scrolls the last one off. And what it's using here is Intuition's own image structure, just like we use Intuition's own border structure. An image extends the graphics image structures in the graphics libraries to allow for graphic images to be placed on any Amiga screen regardless of its bit depth. So we'll go ahead and let this take and stop here, and we'll go in to look at what DrawStage is all about. And this is actually the first part of, excuse me, this happens too. We're still debugging things, so let's just let this thing go. Apologies, folks. This will happen quite a bit throughout the series. There is no memory protection, so, it happens. We just reboot and go on our merry way. It's a good thing here that it doesn't take long for the system to come up, even though with my 1986 configuration, ironically, I'm booting from floppy. So come back, and we will go to Workspace here, and go to PAC-MAN, and we'll look at DrawStage. And this time we will open up the source code for DrawStage right here, and we'll see how graphic images are actually put together. And this is the routine that basically takes and draws out the individual stage graphics. We see all the usual suspects here for our test harnesses, our screen definitions, our fonts, our color tables. But now we start to see actual graphic data, and you'll see references here to bitmap data, and you'll see binary digits over here, you'll see hexadecimal digits over here, and you'll see references to what are called bitplanes, as well as the individual structures for image. Just like we have with border, we have them for images as well, specifying where these images should be placed relative to where we're asking them to be placed with DrawImage. The width and the height of the image, as well as the depth, meaning the number of bit planes, potentially the number of bit planes that need to be drawn, and pointer to the bitmap. And then we have what are called plane pick and plane on and off. And these are actually explained in detail on page B7 of the Amiga Intuition Reference Manual. And if we actually go to that, you'll see that inside of the header file, you'll see a description of what plane pick and plane on and off variables work and how they work. And they are here essentially to specify 2 things. One is the actual bit planes that are required in these images, and for any planes that we don't have selected, what we want to do with them, whether we want to render them as all zeros or all ones. And this is important here because look at the key, for example. The key right here has no bitplane 0. It's not there. We don't have to take and waste memory for it. We can just skip right over it. But there is a plane 1. Plane 1 contains the body of the key, but we also have a plane 2 that has the top of the key in a different color, and plane 3, which has the bottom of the key, which is also in a different color. So we specify that we don't have that bit plane 0. Well, that's 0E. So all this is a bit field. All we have to specify is that we don't have anything except we don't have bit plane 0, but we have bit planes 1, 2, and 3. And that allows us to not waste space inside our data to store the bits for that particular bit image. And we do the same for all of the rest of these images. But let's take a little bit of a sidestep here and show what bitplane graphics actually are. Because probably a number of you who have done software development have never heard the term and are not familiar what this actually means. For that, I actually took and built a special little tutorial here called Planes, which takes each of the individual stage graphics here and breaks them apart into their appropriate bit planes right here. Over here on the right-hand side, we have all of the colors that we currently have allocated for this color palette. And since this is a 16 color screen, we've got colors 0 through 16. Color 0 is black, so you don't see it there. Okay, it's just the background, and we're all the better for it. But you can see now that this cherry graphic, for example, with all of its bit planes on, is actually made up of 3 separate bit planes. Bit planes 0, 1, and 2. You can see that bit plane 1 here has the body of the cherry, and so that corresponds to color number 2. And you can see that the highlights are here in bit plane 0 here, which means if we take and combine them together, we have pixels here, but we also have pixels here too. So 0 plus 1 here, 1 plus 2 gives us color number 3 for the highlights. See? Now you can see that the stem is present, the pixels for the stem are present in all 3 bit planes. Therefore, if you take and combine all of these together, that is 1 plus 2 plus 4, that will give you color number 7, which gives us our brown color. The same process is repeated for all of the other graphics here too. So you can see everything split out, and you can see how the individual bit planes come together to produce the final image. And this tool also serves another function here too. You'll notice that some of these graphics have little glitches in them where I've transcribed the bits incorrectly, and this will allow me to take and find them and correct them. So that's Amiga bit planes in a nutshell. You can see other descriptions of this inside the ROM kernel manuals, inside of the libraries and devices volume, and in many other places that talk about Amiga graphics. But I wanted to take and give a good visual example of how the Amiga bitplane graphics actually work. We'll go ahead and close this now. The next one that will load here, which by the way, I did all these here. All of these are using standard operating system procedures and calls here, so that even though this game is here, it's rendering on its own screen, I can still come back here and I can still do stuff back here. I can multitask, the game will run, it's none the wiser. Okay? This brings us to our next, which is the first animation test that I'm doing for PAC-MAN himself. I'm going to be experimenting over the next few weeks here as I get the time to take and implement this, different animation techniques for handling Pac-Man. If you remember inside of the graphics, all inside here, inside the graphics here, you'll see that there are different types of graphical elements, what they call gels. And you can either control the individual sprites in a what are called simple sprites. You just take and allocate a sprite from the operating system, say, hey, I've got this sprite, nothing else can use it. Then you can take and deal with the sprite directly. You can change the sprite dimensions, you can get the sprite, you can move the sprite around, and when you're done, you can take and free the sprite so that other applications can use it. And this is an example, essentially, of using the operating system at its most basic level to just take and allocate resources so that you have that resource and other programs can't stomp on you for using that resource. At least well-written programs anyway. So with this particular animation test, I'm using the simple sprite technique. And it is actually described inside the ROM kernel manual. It talks about how you take and set up a simple sprite structure and the data that that simple sprite structure actually needs in order to function. In this case, we have our Pac-Man sprites. And the way sprites are basically set up in the hardware, they're interleaved. Sprites on the Amiga are 16 pixels long, 16 pixels in width. 16 pixels in width, and they can be they're essentially allocated 4 colors, but the first color, color 0 for the sprite, is transparent. And in this case, they're set interleaved. This particular sprite is Pac-Man. Pac-Man only needs 1 color here, so we only use one of the bit planes and leave the other one empty. The simple sprite structure, if you look inside the ROM kernel manuals also, just has these reserved areas right here at the top and the bottom of the bitmap data, which are used by the simple sprite state machine inside the ROM to take and maintain position. And the reason for this is actually going to become important in just a second. But we'll see that we have a number of Pac-Man graphics all done out in manner similar to the stage graphics. We have a simple sprite structure that basically specifies where the data needs to come from, the height of the data, 16 lines long, and where the initial position is going to be. I just put it there at 64 by 64 as an example. And just an internal counter value. This will actually get changed as getSprite gets called. And again, all we're really doing here, coming in, opening everything up, making sure everything's open. And once everything's open, we just take and get the sprite. We get the sprite and say, okay, what we get back is the sprite number of what we've got. Okay, operating system says that's successful. Okay, great. We then take and, yes, you're supposed to check as to see whether or not you actually got it. I didn't in this case, just for the sake of simplicity. But we do a little bit of math. And this is also completely explained here in the Libraries and Devices manual. Completely. In the examples that you have here, because there's a complete example that you can use to start with here. And this was pulled directly from that example to say, okay, given that sprite, what color registers do I have access to? Well, this gives us the start of our color registers. And so I just take and set RGB 4 so I get this nice yellow color. I could just as easily take and use load RGB 4 to do this as well, but I did it here for illustrative purposes. I set the colors, set an initial X position, and then I immediately take and go into a loop where we march Pac-Man across the screen. It looks like this. This is simple sprite control within the operating system entirely on its own here. And you can see it works just fine. It has some interesting quirks, which I'm going to show you now. We'll take and rerun this demo here and let this just let this pause through here. The operating system is taking care of positioning the sprite. Positioning the sprite, dealing with the copper lists, getting all of that set up for you, such that even if I take and move this window here with the move sprite here, you'll notice that Pac-Man's position, it's changed. But the moment that that stops, you'll see that the sprite is just here. It's above everything else, so yes, it's bleeding through to the other screens here. But while it's within the move sprite, create sprite loop and everything, it's taking care of dealing with its relative position relative to where you're at, where your screen actually is in intuition. As you can see, it works extremely well. One of the things that it does here, so we go into a loop that basically takes and changes the sprite animation to match one of the sprites that we have above, one of the 3 animation frames. We go ahead and move the sprite forward 1 pixel while we're at it, just as simple as possible. But you'll notice that we have what's called wait TOF. Wait TOF is defined in the graphics library, and it's a very simple routine. All it says is it marks this flag, this task, and says, make this task wait until the top of the very next frame. That's it. Click, click, click. It provides a nice way to synchronize to the frame output. If we didn't do this, it would go very quickly. But there we go. Just a nice way to render out very quickly, do some very simple animation. And this is all relative to the task. So wait TOF just tells this task to do it. So as we take and move Pac-Man's animation routines and whatnot into its own task, it will maintain frame synchronization entirely within the context of that given task for us. Finally, we go ahead and move the sprite here like you saw before, just so we could take and demonstrate the overlay effect that sprites normally have. Finally, when we're done, we just take and free the sprite. We're done with it. Give it back to the operating system. Remove our font. Close everything down. That's it. I'm going to end here by basically showing you that that we've got all of these various different things that we've done here, all these different test harnesses and whatnot. And I can turn right around without thinking about it too much. I can run it on different system configurations. I'll take and run it on my Amiga 3000. We'll boot it up into version 2.0 here really quickly. And then I'll just take and insert a disk that contains our Pac-Man tests. Same folder as we had on the other workstation here. That's the PC coming up. Okay, and then I can take and go through and run like DrawMaze, for example. And you'll see it runs just fine over here on this machine. Okay, it's great. It works. It just works. You can see the DrawStage works similarly. Or not. Okay, I didn't update this guy with the new code. My bad. Okay, I'll just reboot. No big deal. My bad. Okay. That's a weird little mistake on my part. We can see Sprite Pack. Sprite animation. It's working just fine. Nice and multitasky. Everything's groovy. And you can see the same overlay effect happening here as well. And you can see the planes tool here working just fine as well. So you can see all these things working no matter which version of the operating system, which system configuration we happen to choose. This is ultimately the reason for using the operating system routines. And you can do this in a very efficient manner. As we delve further into this particular series, you will see that the operating system routines, as provided by Commodore Amiga, were neither bloated nor slow. They're very efficient. So with that, let's go ahead and end it here. Until next time, guys. Have fun.